Swayam Prabha. Digital India. Educated India.
Good morning, students. So, in the last lecture, we introduced ourselves to the idea of running time complexity. And we also introduced ourselves to the concepts of different cases of running time complexity, such as the every time, the every case, time complexity, the worst case, time complexity, average case, time complexity, and the best case, time complexity. And each of them had their own denotations. And we took various examples to estimate the running time complexity for the different algorithms. Today, we will move a bit further and introduce ourselves to the concept of complexity functions. So, by complexity function, we mean a function that maps positive integers to non-negative reals. It maps positive integers to non-negative reals. Examples: so all these are examples of complexity functions. So basically, it will map a positive integer into a non-negative real, okay, in each case. So typically, standard notations of complexity functions are, of course, this is not sacrosanct, you can use your own notations, but typically we will refer to complexity functions by denotations like Fn, Gn, etc. Now moving a little further ahead, we try to define some more concepts. Linear time algorithms. Okay, a linear time algorithm is an algorithm for which the running time complexity is linear in the input size. So the running time complexity is linear in the input size. Likewise, you can define a quadratic time algorithm as the running time complexity for such algorithms is quadratic in the input size. Okay. So while a linear time algorithm, the running time complexity is linear in the input size, for a quadratic time algorithm, the running time complexity is quadratic in the input size. And in all complexity analysis, we are interested in studying the eventual behavior. We will see this in a moment with an example. Okay. So, and when we consider this eventual behavior, there is one fundamental principle that you need to remember. So this is a very important fundamental principle that will come time and again in all your analysis. Any linear time algorithm for a given problem will be eventually better than a quadratic time algorithm. Okay, so the idea is that any linear time algorithm will be, for a specific problem, for a given problem in hand, will be eventually better than a quadratic time algorithm. Better, or like whatever we have been studying so far, efficient or better than a quadratic time algorithm. We will soon see an example for this. Let's say that there is a problem P, okay, and we have two algorithms. Let's say one is called A and the other is called B, to find a solution for the same instance of the problem. Okay. Now you are given that the complexity or the running time complexity, so we will use complexity for short all the time. Okay. So the complexity of A is say 0.1 n square. Okay, and let's say the complexity of B is 100 n. So by definition, just now we have learned that this is a quadratic time algorithm and this is a linear time algorithm. Okay, and we can claim that algorithm B will be better than algorithm A, better or efficient than algorithm A if 0.01 n square is larger than 100 n. And if you divide both sides by 0.01 n, then for n larger than 10,000, B will be more efficient than A. So that is why we were telling that B will be better than A, okay, or more efficient than A eventually. So for large n, okay, this is where what we mean by eventually. You see, like for n larger than 10,000, B is going to be better than A. Now it might be that in your application, in an application that you have chosen, the value of n never goes beyond 10,000. In that case, the algorithm A will be better than algorithm B and our choice will be algorithm A. However, if you know that n is going to get larger and larger soon, then algorithm B is a better choice for obtaining the solution. Now, once we have talked about linear time and quadratic time, we need to further understand a nuanced difference between a pure quadratic function. So here by function I mean read as complexity function that we have discussed just now. Pure quadratic function, okay, versus a complete quadratic function. So a pure quadratic function is a one which does not have any linear term in it. Example 5 n square. or 5n square plus 100, etc. Okay. Whereas a complete quadratic function will have a linear term in it. Example would be now let us compare a table of values which changes with n. In one column we have 0.1 n square, and in the other column we have the expression that we wrote just now. So note that this is the pure quadratic function. I'm sorry. Okay, we can probably rewrite. N so this one is a pure quadratic function, whereas this one is a complete quadratic function. Now let us say we vary the value of n. If we do so, 0.1 n square will be 100, will be 10 in the first case, 40 in the second, 250 in the third, 1000 in the fourth, and 100,000 in the fifth case. If we compute the complete quadratic function, then the values that come up are as follows. Now you see the interesting trend here. As you increase the value of n, okay, as n increases, the pure and the complete quadratic functions come closer and closer. Okay, and this is what we were trying to mean by eventual behavior. So eventually they tend to be almost the same. So while initially with the value of n there was a substantial difference between the pure and the complete quadratic functions, as soon as we started increasing the value of n, the difference between the pure and the complete quadratic function started diminishing. Okay, this is what we meant by the eventual behavior that I was talking about. So what does then this mean? So this actually gives us an interesting, a very interesting indication, and the indication is that although 0.1 n square plus n plus 100 is not a pure quadratic function, but this can be approximated by a pure quadratic function eventually. So a complete quadratic function can be eventually approximated by a pure quadratic function. And this is one of the crux of the things that we will be studying now. So this means that if, say, there is an algorithm A which has a running time complexity of 0.1 n square plus n plus 100, then we can say that A will eventually be a quadratic time algorithm. Okay, because as we have seen from the table that the 0.1 n square and 0.1 n square plus n plus 100, the difference diminishes as the value of n increases. So therefore A will eventually reduce to a quadratic time algorithm, a pure quadratic time algorithm. This brings us to a very important notion in complexity analysis. So complexity functions that can be classified with pure quadratic functions are called theta n square. Okay, so you pronounce this as theta, okay? Theta of n square. So suppose we have some function gn equals 5n square plus 100n plus 20. We can, since this can be eventually classified by a pure quadratic function, we can say that Gn is theta of n square. We will come to a more rigorous definition of theta soon, but this is like the first level idea in terms of complexity functions. Recall the exchange sort complexity. Exchange sort every case complexity. What we found, Tn is equal to n into n minus 1 by 2. This is nothing but n square by 2 minus n by 2. And as we said that this complete function will, for some large value of n, eventually turn into a quadratic function, and therefore we can write Tn is theta of n square. In other words, any quadratic time algorithm is also termed as theta n square algorithm. Okay. Similarly, complexity functions that can be classified by pure cubic functions are said to be theta n cube, and so on and so forth. Okay. So each of these classes are called complexity categories. And as you can immediately understand that there can be different complexity categories. For instance, where this sign indicates that eventually theta n will be larger than theta log 2n. That is, eventually theta log 2n will be more efficient than theta n. Similarly, eventually theta n will be more efficient than theta n log 2n. So this is eventually more efficient. Similarly, in all other cases. Okay. In fact, if we draw the growth of these functions, we will immediately able to visualize this observation better. So let's say this is our n, 0, 1, 2, 4, 8. So these are in steps of powers of 2, 32, 64, 128, and so on and so forth. This is a logarithmic scale. The drawing is perhaps not perfect, but I guess you get the idea. So you see, eventually at some point or at some value of n, log to n is going to be better than n, and n is going to be better than n log n, and so on and so forth. So with this idea in place, we will now introduce ourselves to what is called order. So here we will first start with the upper bound or the big O notation. Definition. For a given complexity function, say Fn, big O of Fn is the set of complexity functions Gn for which there exists some positive real constant C and some non-negative integer n such that for all n greater than equal to capital N, Gn is less than equal to C into f of n. This is also sometimes denoted as Gn in big O of Fn. Okay, so if there exists a complexity function, a set of complexity functions, okay, Gn, for which you can find a real constant C and some value of n, okay, such that all n larger than n, we see this condition gn less than c of fn, okay, to be true, then we say that gn is big O of fn, okay. So this term gn is belongs to fn is read as gn is big O of fn. So pictorially, if you try to draw this phenomena, say n is here, then so see, after the value of capital N, okay, C into Fn is always larger than Gn. So Gn always lies below C of C into Fn. So Gn lies below C into Fn for all n greater than equal to n, right? So this is the interpretation of big O. That is as if Gn is upper bounded by C of Fn. So this is sometimes also called the upper bound. So Gn is upper bounded by C of Fn, okay. So let us take some example and try to get the concept further clear. So recall the exchange sort. So the every case time complexity for exchange sort was Tn equals to n into n minus 1 by 2. Now consider n to be greater than equal to 0. Then you can always write n into n minus 1 by 2 is less than or equal to n into n by 2, that is half n square, okay. And this immediately tells you that Tn is big O of n square for C equals half and n greater than equal to 1, okay. For all n larger than 1 and the choice of C equal to half, we have the above condition holding, and therefore we can say that Tn is upper bounded by n square, or Tn is big O of n square. One more example. Show that n is big O of n square. Okay. Consider n greater than equal to 1. So you can always write n is less than equal to 1 into n square, and therefore for C equal to 1 and capital N equal to 1, we can say n is big O of n square, right? So here C is the constant, and for any n larger than equal to 1, we have the condition satisfied, that is Gn less than equal to C of Fn. Okay, and therefore we can write that n is big O of n square. So since we are interested in the eventual behavior, the upper bound that we studied is in general called the asymptotic upper bound. Okay, this means that we are interested in the eventual behavior. Just as asymptotic upper bound, we have a similar concept called the asymptotic lower bound. Okay, let us now define the asymptotic lower bound. For a given complexity function, Fn, omega Fn is the set of complexity functions Gn for which there exists some positive integer C and some non-negative integer n, such that for all n greater than equal to n, Gn is greater than equal to C into Fn, or we write Gn is in omega Fn, okay, or Gn is lower bounded by Fn. So again we can very nicely pictorially describe this. So here the interpretation is that Cfn will eventually always lie below Gn. So now let us look into some examples of lower bounds. Again, consider the exchange sort case. For n greater than equal to 2, we can always write, so this is a trick we are playing, see, you have to play similar tricks when you have to actually estimate the upper or lower bounds. Okay, so you have to learn. So the more you will practice, the better you will be able to solve this kind of problems. So we can write n minus 1 is larger than equal to n by 2 for all n greater than equal to 2. So this immediately says that n into n minus 1 by 2 should be larger than equal to n by 2 into n by 2, that is 1 by 4 n square. So thus for C equals 1 by 4 and n equals 2, we have Tn in omega n square. So see, this is one algorithm, the exchange sort algorithm, that is both in big O of n square as well as in omega of n square. Of course, for different constants and different values of capital N. One more example. Show that n cube is big O of n square. Okay. Again, this is easy. For n greater than equal to 1, we can always write n cube is greater than equal to 1 into n square. Therefore, for C equals to 1 and n equals to 1, we have n cube in omega n square. Okay. So in this way, we can solve such order estimation problems. Okay. Finally, we are in a position to formally define theta. Okay. So for a given complexity function, Fn, theta of Fn is equal to big O of Fn intersection omega of Fn. So in other words, we can write that theta Fn is the set of complexity functions Gn for which there exists some positive constants C and D and some non-negative integer n such that for all n greater than equal to n, we have C into Fn less than equal to Gn less than equal to D into Fn. Okay. In such cases, Gn is said to be theta of Fn, or Gn is order of Fn. Now, if you combine the two plots that we saw just now for the upper bound and the lower bound, then from there you easily can get the notion of theta n. Let's say this is our Gn, okay, and let's say this is our Cfn, okay, and let's say this is our D of Fn. Okay, so in this case we can say that Gn is order of Fn because Gn, you see, lies between some C into Fn and some D into Fn. So it is bounded on both sides. So in the upper bound it was bounded on the upper side. In the lower bound, it was bounded on the lower side. Now it is bounded on both sides. So the every case time complexity for exchange sort actually is an example of this kind of a function, as we have just now seen. Now we will solve one more intricate case. Suppose I ask you to show that n is not in omega n square. Okay. If we have to show this, we will approach the problem from proof by contradiction. Okay. So this means that we will assume that n is omega n square and then prove that this cannot be true. So if we assume that n is omega n square, is in omega n square, then we can write that n is greater than equal to Cn square for some positive constant C and all n larger than equal to n. Okay. So if you divide both sides by Cn, we have 1 by C greater than equal to n, which means that for any n larger than 1 by C, this inequality will not hold. Okay, and that further means that it cannot hold for all n larger than equal to some n, because then from that point onwards, from that capital N onwards, for all other cases this has to hold. However, we have seen that it will not hold for any case larger than 1 by C. Therefore, this is bringing us to a contradiction, and we obtain that n does not belong to omega n square. Okay. So there is a final definition with which we will end this chapter, which is a little more strict version of the upper bound definition that we saw just now. For a given complexity function, Fn, small o of Fn is the set of all complexity functions Gn satisfying the following. For every positive real constant C, there exists a non-negative integer n such that for n greater than equal to n, Gn is less than equal to C Fn, or Gn is small o of Fn. So note the important distinction. So for big O, we did not have this specific condition here. So this has to hold for every positive real constant. For big O, we have to find one positive real constant. For small o, we need to find such an n, such a capital N, for which any positive real constant C we consider, Gn is going to be less than equal to Cfn. Okay. So this is also sometimes called Gn is small o of Fn. Similarly, exactly similarly, you can also define the concept of small omega Fn. Okay. Just like small o of Fn. So just to see the concept a little bit more clearly, let us say we are asked to show that n is in also small o of n square. We have already proved that n is in big O of n square. Now we are asked to show that n is in also small o of n square. Okay. Let us assume that C is greater than 0 is given. Okay. So we have to find an n such that for all n greater than equal to n, n is less than equal to Cn square. Now if we divide both sides by Cn, we have 1 by C less than equal to n. So therefore it suffices to choose any n, any capital N greater than equal to 1 by C. If you choose any capital N that is greater than equal to 1 by C, the above condition is going to hold and n is going to belong to small o of n square. So this brings us to the end of the first chapter on algorithmic efficiency, complexity analysis, and concepts of order. So I would invite all of you to practice more and more problems related to finding the every case, and if not possible in certain algorithms, worst case, average case, and best case time complexities. Take some very simple algorithms that you have implemented in your programming and data structure course and try to find out whether you can have an every case complexity for it. If yes, very good, compute it. If no, see if you can find out the worst case and the average case time complexities. And similarly, also practice how to obtain the big O, omega, order, that is theta, small o, and small omega of different complexity functions. Okay, these are some of the practice problems that you should be doing. We shall do a lot of such practice problems in the tutorial classes. In addition, we will also share materials with you which has lot of such practice problems. Okay, but so the main crux of understanding this chapter is to solve more and more problems. Okay, the more variety of problems that you solve, the better it will be for you to understand the concepts. Thank you.